My name is Mark Vincent Yason. I am part of the X-Force Research and Development team. So I work for the BPS technology. Basically, BPS is a behavioral antivirus. So what I do, my day-to-day job involves analyzing a bunch of malcodes and then attempt to generate a behavior pattern for it, so that if a new malcode attempts to use this new technique, this specific technique, so they will be detected. So from time to time, my work involves tracing packers. This is for malcode analysis, for posting malcode reports, or for engine support. So I work with developers developing the engine. So I trace the malware and identify what it does, and then tell the engine developers what it does, and then try to support the particular packer. So my talk is about reversing tricks employed by packers. So packers are one of the most interesting things in the interesting puzzles to solve in the reverse engineering field. So most of them some of them are created to protect legitimate applications, but they're also used by malcode. So over time, researchers on the other sides, the one who developed the packers, they develop anti-reverse engineering tricks, while reversers on the other side, like malcode analysts, find ways how to break these protections. So anti-reverse engineering tricks are also interesting to look at, because we gain a lot of knowledge about Windows internals. So this talk focuses on commonly used and interesting anti-reverse engineering techniques employed by packers. It also discusses ways on how to bypass and disable this anti-reversing tricks or techniques. So this is what you use if, for example, automation tools like failed, or you are an antivirus. If you are a researcher helping engine developers to tell them what the packers tries to do. So information presented can also be used in identifying and solving anti-reversing tricks. So my talk is divided into several parts. The first part involves debugger detections. It is how packers attempt to detect the debugger, or if a debugger is running the system. The other one involves identifying breakpoints or patches in the packer stub. And the next one is anti-analysis, and the others and advanced techniques used by packers. And I will also briefly discuss about the tools that can be used. So the first one is debugger detections. So the first technique is the most basic and the most obvious anti-debugger detection technique. So this one just checks the being debugged flag of the PEB. So the PEB can be so FS 30 points to the PEB. So the API is debugger present, check this particular flag. So because this check is very obvious, so some packers try to obfuscate it. So this is an example call. So the packers try to call is debugger present. If it's returned a non-zero value, it means the debugger is detected. And the other one particularly directly checks the PEB for the being debugged flag, and then just branch if a debugger is found. So this particular debugger detection technique can be easily bypassed by patching the PEB being debugged flag, or you can use OLE script to patch it automatically by the DBH command, or OLE advanced. It is an OLE DBG plugin that you can use to automatically patch this flag. So the next one is one of the not really documented debugger detection technique. So when you load when a program is loaded by a debugger, when a program is not loaded by a debugger, usually the PEB anti-global flag is set to 0, but it can be overridden by a register entry or T flags. So if the program is loaded by a debugger, usually it will contain 70 in as its value. So packers can identify if a debugger, if the program is being debugged by checking this flag. If it contains a non-zero value, it means that the process is probably being debugged. So other flags that the packer can check is the process heap flags. Basically, because the flags are set in the anti-global flags, the initial heap created for the process heap, well, it's usually 2 if the process is not being debugged. But if the process is being debugged and anti-global flags has a different value, so process heap flags will contain a value different from 2. So usually packers will check the anti-global flag and also check the process heap flags or the process heap force flag. It will check if flags is 0 or force flags is 0. So this is an example how to patch. This is an OLE script a sample how to patch the anti-global flag and the process heap flags and force flags. So it just retrieve the PEB and then patch the anti-global flag with 0, and then retrieve the process heap and then patch the flags and the force flag fields to 2 and 0, like the process is not being debugged. So, by the way, in the CD there will be a white paper there that contains the sample codes. So, another debugger detection technique is via the debug port of the eProcess kernel structure. Basically, if the process is being debugged, the eProcess debug port field will contain if the process is not being debugged, the debug port will contain 0. Otherwise, it will contain a non-zero value. So if you are a packer, and if you want to check it using in the native layer, in the NTDL layer, you can query the debug port field using a NT-query information process with the process information class equal to process debug port. And if returned -1 in the return variable, it signifies that the process is probably being debugged. So in the kernel 32 layer, you can use a check remote debugger present. Basically, it just calls the NT-query information process to check if a particular process is being debugged. So one way to solve this is another OLE script sample. What it does is to try to set a breakpoint in NT-query information process and then find the point where it tries to return. And then it will set up a breakpoint handler. So in the breakpoint handler, it will try to check if the process information class being passed is process debug port. If that is the case, it will try to patch the returned process information to 0. So it will try to fake the return value of NT-query information process. So debugger interrupts. So by default, a single step and breakpoint exceptions generated by int1 or int3 is not passed to the exception handler. So if after the int1 int3 instruction, the exception handler is not invoked, it means that the process is being debugged. So flags can be set inside the exception handler to mark that it had been executed. So there are times that packers use debug break instead because it uses int3, it invokes int3 also. So here's an example. So in this example, you will see it's about to invoke entry. So the technique here is that this is a sample code I did. So the technique here is that if the process is being debugged, after I step through the entry EAX, if the process is not being debugged, after I step through entry, EAX should be changed to -1. But if you just trace it, like you press F7, so it will just say entry command at debugger, then address, and then EAX is not modified. So it means that you will be detected. So it says that it had detected the debugger through a debugger interrupt. So one way to solve this is to when it displays entry command at the debugger address, you can try to go to the exception handler by a view, and then SEH chain. So this one is the exception handler in the top of the chain. So you just double click it, and then set a breakpoint in it, and then you will need to pass the exception generated by entry to the exception handler by pressing Shift F9 here. So you are now in the exception handler. So before continuing, what is a context? Basically, a context contains the current state of the thread. It can be retrieved by a get thread context, but it is also passed to the exception handler via the context record parameter, and then it contains the state of the thread when the exception occurred. So basically, some packets try to use the context record passed in the exception handler, for example, checking the debug registers, and then manipulating the return the EIP when the exception handler returned. So in this example, you are now in the exception handler. So EAX will contain the context record. So it will modify EAX. So EAX plus B0 contains the context record and then the EAX register. So it will try to change the register when the exception handler returned. It will try to change the context of the thread that causes the debug exception. So it will change the EAX to -1, and then increment the EIP, which is EAX plus B8. It contains the context record, EIP. If you can see here, it will change the EIP. It will increment it by 1. So it means that when the exception handler returns, control will transfer to this address. So you just press Shift F9 again, and then you will be transferred back here. And then EAX will now contain the correct -1 value. So you can do this because the debug exceptions are not automatically passed to the exception handler. You can make it automatically pass to the exception handler by checking this checkbox, entry breaks and single step breaks. So when you step in entry, it will automatically call the exception handler instead of you just tracing it. So this is the solution. So another debugger detection technique is because several CPU cycles are spent